Bonjour à tous. Okay, welcome to another video in the series on physical chemistry. Right. So this topic is chemical equilibrium, which mainly talks about the reactions that are reversible. So some reversible reactions that you should have already come across are things such as maybe weak acid or weak base, which dissociates / ionizes partially in water, and therefore you put that reversible arrow sign, right? Another one would be the Haber process, which is the synthesis of ammonia gas from nitrogen and hydrogen gas. So take note that the reversible arrow is written this way, right? And not any other way. Okay, so some formal definitions before we go into calculations and stuff. So what exactly is a reversible reaction? That is a reaction whereby the conversion of the reactants to the products and back, products to reactants, occur simultaneously. Means that it's always happening at the same time, right? It's not that, oh, okay, we go reactants to products first and then products become reactants. No, it happens all at the same time. Okay, until this state known as dynamic equilibrium is reached, which means that the rate of the forward reaction and the rate of the backward reaction are the same and they exist, so they have to be non-zero. And this results in, and then we know that it is dynamic equilibrium when there is no net change in the concentration of reactants and products. The keyword here is net because let's say I have two classrooms of 30 people each, right? So now it's at kind of like equilibrium, right? 30-30. So if one student A goes from class A to B and student B moves from class B to A, what happens is that there's no net change in the numbers, right? But there is a change because now student A is in class B and student B is in class A. So there is a change, but there is no net change in the number. And why this is important is because we don't label our chemicals as A and B, right? We don't call them like Mary or Tom or Sam or something, right? So no net change, right? We just look at no net change. Now the main governing principle is Le Chatelier's principle, which is commonly abbreviated as LCP, which you can write in your exam. It's accepted, right? So LCP states that a system at equilibrium, and at equilibrium, it must be at equilibrium, is subject to change. The system responds by counteracting the effect of the change by re-establishing the position of equilibrium. So what this means is that if say I increase the temperature of the system, like I am the one who increases the temperature of the system, the whatever reaction itself will want to reverse that change. And how it reverses that change is that it will try its best to reduce the temperature, right? And how it reduces the temperature is maybe say an endothermic reaction, because endothermic reaction absorbs the heat energy from the surroundings, and therefore it absorbs the thermal energy from the surroundings into the system, and therefore the surroundings will decrease in temperature. Okay, so I'm going to explain all of this, but when you look at this on your own, you can use the AABB equation here to rationalize what's going on. Okay, so the first factor is concentration. So what this means is that, let's just say I have a Haber process, right? Haber process is N2 plus H2 2NH3. Okay, so let's just say I add nitrogen gas to the system. LCP wants to reverse that change. So I want to decrease the concentration of nitrogen now. And how can I do that? I just use up the nitrogen now. So the position of equilibrium will shift to the right to decrease the concentration of the reactants. If now I were to decrease, decrease the concentration of hydrogen, LCP wants to reverse that change. So it wants to increase the concentration of hydrogen. So the position of equilibrium will now shift to the left and the products will now be converted back to reactants. So this is a qualitative treatment. As of now, we'll talk about the quantitative later on, but as of now, you can think about this way to predict what happens in a reaction, because I mean, you can say, okay, yeah, so it reverses the change by decreasing nitrogen, but don't I decrease the hydrogen as well, right? So that's a valid question, which we will look at later on how to determine how much is enough, right? Next, let's look at total pressure. So total pressure affects only gases, right? So if you have solids or liquids, don't care about them, right? Just think about the gases. So back to Haber process, N2 plus 3H2. 2NH3, right? So how many molecules of gas are there on the left? There are 4. On the right, there are 2. So if I were to increase the pressure of the system, what does this mean? The particles are now closer together, right? If they're closer together, how do I reverse the change? If I want to decrease the pressure, I just need fewer number of gaseous molecules, right? Because if there are fewer collisions, there's less force acting on the walls of the container, and therefore there is a decrease in the pressure. So how we can do that is to shift to the side with fewer number of moles, which happens to be the right hand side. So if I were to increase the pressure of the system, the reaction will favor the forward reaction and move to the position of equilibrium shift to the right. So there's a net decrease, right? It goes from 4 to 2, right? For every mole, for every 4 moles, there is now 2 moles. There's a net decrease of 2 moles, right? Now, if I were to do the reverse and decrease the pressure of the system, now LCP wants to increase the pressure of the system, and that you can do that by shifting to the left, by producing more gaseous molecules. In the event whereby they have the same number of molecules, right, then there'll be no change, because whether I shift to the right or I shift to the left, it's not going to change anything. So if it's not going to change anything, why do I want to waste the effort to do something about it, right? So no change. If the number of gaseous molecules on both sides are the same, the position of equilibrium will not be affected by the change in pressure. Okay, next let's look at temperature, right? So as I said at the start, if I have an exothermic reaction, exothermic reactions will increase the temperature of the surroundings, which is useful to reverse a decrease in temperature, right? So let's say I have a reaction now. Can't think of reaction, but let's just say I have A plus B forms AB, and this is a exothermic reaction. The forward reaction is an exothermic reaction. So this thing here always describes the forward reaction. So if the forward reaction is exothermic, it means that the forward reaction will release heat to the surroundings and increase the temperature. So now if I decrease the temperature of the system, LCP wants to reverse that change by increasing the temperature of the system, which can be done by favoring the forward reaction. If now I increase the temperature of the system, LCP wants to decrease the temperature of the system, and you can do that by favoring an endothermic reaction. If the forward reaction is exothermic, the backward reaction is endothermic. So when I increase the temperature of the system, I will favor the endothermic reaction, which is in this case the backward reaction. So the position of equilibrium will shift to the left. So actually, it's up to you whether you want to describe it in terms of shifting left or right, or you want to say, oh, it favors the forward reaction or it favors the backward reaction. As long as there is some hint in your answer as to where the equation runs towards, right? Okay, now addition of inert gas. Addition of inert gas is a particularly interesting case, right? So when you add the inert gas, it means that the system is already there, and then you just pump in more gas, right? So if I were to keep it at a constant volume, what changes? Constant volume means that the pressure must increase, right? Now the pressure increases and the amount increases proportionally, right? And the concentration of everything doesn't change, because if you think about it, partial pressure is number over total number multiplied by total pressure. So if everything increases, right? If total pressure increases and total number increases, then actually this change is kind of nullified, right? So there's not much change in the partial pressure. So if there's no change in partial pressure, the position of equilibrium is not affected. But if I were to now do it at constant pressure now means that the total volume must increase, right? So the total pressure remains the same. Wait, I forgot to change the color. So the total pressure remains the same, but the total number of moles increases. And this means that the partial pressure actually decreases, right? And if partial pressure decreases, now I want to favor the side that increases the concentration, right? So it shifts to the side with more number of gaseous particles. Okay, catalyst. Now remember that reaction at dynamic equilibrium is one in which the forward and the backward reaction occur at the same rate. So if I add a catalyst, I will increase both of the rate by the same amount, right? So if the forward becomes faster and the backward also becomes faster, the rate is they're still the same, right? So if they're still the same, the position of equilibrium does not change, and therefore the catalyst does not affect the position of equilibrium. But what changes is that the equilibrium is achieved faster. Right? I mean, this is assuming that it's not already at equilibrium. If it's already at equilibrium, then yeah, nothing will happen, right? There'll be no net change, not nothing will happen. There'll be no net change. Okay, now let's try to do this quantification. So previously I said, okay, yeah, I shift to the right, but if I decrease one, won't I decrease the other at the same time? That's a good point. So there are two main ways. There are two ways to do this. It all encompasses the idea of a ratio, right? So we can do dynamic equilibrium by ensuring that this ratio is kept constant, and this ratio is unique to each reaction and unique at different temperatures. So this ratio is only affected by temperature. So I think we know how to find a ratio, right? Okay, so it's always products over reactants, right? Products over reactants. And we raise the concentration of the particular thing to the power of the molar coefficient. So in this case, it's C to the power of small c and D to the power of small d, blah, blah, blah. Now the reaction quotient, QC, is the ratio at any point during the reaction. So if I measure it now, I measure it 5 minutes later, I measure it 10 hours later, that's the reaction quotient. Now, equilibrium constant is the ratio at dynamic equilibrium. So this ratio does not change and only changes with temperature. This value here is a constant as stated in the name, and this constant is the one that tells us, so does the reaction now move forward or backwards, right? So let's just say that the Kc of a reaction is equals to like 2, okay? And we now calculate that QC now at this point in time is 1. Remember that the ratio is always products over reactants. So if it's 1, now the QC is less than the Kc. If it's less than the Kc, it means that now there is not enough products on top and there are more reactants at the bottom. So this means that now I want to produce more products, right? So to produce more products, the position of equilibrium will shift to the right, so that it will slowly go to 2. So that's how you use the QC and the KC. Okay. I've summarized this over here. You can use the logic of what the ratio means to rationalize what goes on. Now, this is a common question. So what do I include inside this ratio? Do I include everything? Okay, so there are two types of equilibrium. One is homogeneous equilibrium, which is when everything is at the same state or at the same phase, right? I use phase because equals is not really a state, but it's a phase, right? So if everything is equals, then yeah. So in the Haber process, everything is gaseous, right? So include everything up. Now in heterogeneous equilibrium, this means that the substances are at different phases. So usually we would ignore stuff that is a solid and liquid because the concentration of a solid and liquid doesn't change, right? Now, we usually include stuff that is like aqueous, gaseous, but that really depends. So you need to do more of this to figure out, right? And of course, I will have some questions in the future that you can do by, or if you're a member, you might have, you should have access to it, right? Okay, so in this case, notice that I did not include the solid inside. So another point to take note, another point to raise here is that you can also express this in terms of partial pressure. So partial pressure, of course, we only include the gas, right? So partial pressure of CO square over partial pressure of CO2. So the manner is the same. The values would differ, but you're not expected to know how to convert between each of them. Okay, so if the question asks for Kp, write it in terms of the partial pressure of the gases. If they ask for Kc, write in terms of concentration. But you should know that concentration and partial pressure are related, right? From gas laws. If you don't remember, you can revisit that video. So commonly inside questions, you will draw this thing known as an IC table, an ICE table, IC table, whichever how you call it, which is initial change in equilibrium. you can try to keep the units consistent, but always remember that when you plug it back into your Kc equation, it's either in terms of mole per dm cube or in terms of partial pressure if you use Kp. Okay, so now I want to link to topics that we will talk about and have talked about. So if we link this to kinetics, you can watch the kinetics video if you don't know what this is, right? So Kc can also be written as forward reaction, the rate of the forward reaction divided by the rate of the backwards reaction. And you can do the math and figure it out. We can link this to energetics by finding the Gibbs free energy change from the equilibrium constant. This big K, notice this is small k, this is small k, this is big K. Okay, small k is rate constant, big K is equilibrium constant. So this K can be anything, right? When you go to J2, you will look at things like Ka, Kb, Ksp, Kin, or blah, blah, blah. Okay, so this K can be any of these things. But for the purpose of this video, it is Kc. Okay. When delta G is less than 0, Kc is more than 1. And this makes sense, right? Because if the forward reaction occurs, we want more products to always be present than the reactants. So the ratio would always be more than 1. And if, yeah, okay, you can do the math, right? And figure the rest out. Okay, the next tool is kind of like a multi-step reaction, which let's say if I have a dibasic acid. Okay, I know sulfuric acid is a strong acid, but we can always do this, right? So if I have, say, H2SO4 forms H plus HSO4 minus and HSO4 minus H plus SO4 2 minus. So if this is K1 and this is K2, the overall reaction of this, which is H2SO4, forms 2H plus SO4 2 minus. The overall equilibrium constant is K1 times K2. Okay, simple as that. Okay, molar multiples. What this means is that, let's say now I have, okay, let's say now I do Haber process, right? So if I have Haber process, N2 plus H2, 2 NH3. Okay, so this is K1. Okay, if I were to do something like half N2 plus 3/2H2 forms NH3, what's the Kc of this reaction? The Kc of this reaction, notice that this divided by half, right? Or we times half, right? Or divided by 2 or times half, right? So the Kc of this reaction is equals to K1 to the power of half. So you always put it to the power of the multiple, okay? So of course you need to practice more to figure this out, but I hope this video was helpful, and see you in another video.